we are looking for the resultant vector of these two vectors added together, and we want, in the end, the magnitude of that vector and its direction as measured from the positive x-axis, counterclockwise from the positive x-axis. So we were given this coordinate system, x right, y up. R1 is 8 inches long and 60 degrees from the horizontal. And we have vector R2 that has a length of 6 inches. I'm going to do it a little bit different on the board just to illustrate a point here. It's the same information, just presented a little bit differently. Pretend it was given to you as 70 degrees from the y-axis rather than 20 from the x. The result is the same, but just so we can see what the difference is between the two ways we can analyze this. So the premise is we can add, or the resultant is going to be the summation of the two vectors, vector R1, vector R2. Notice in this equation, this is a vector equation. I'm adding a vector that has ij components, or this has ij components. These both have ij components as well. So in order to do this evaluation, I want R1 and R2 in their component form, even though they're presented with a direction and a magnitude. We can start with R1, which looks like the ones we did the other day. How can we express R1 in its component form? So what is the I component of R1? What's the J component of R1? How much of R1 lies along the x-axis? How much of it lies along the y-axis? 8 cosine 60 is going to be the I hat component, so the amount in the x direction. And then the y direction, this leg is opposite the 60, so we can add to this 8 sine 60. And in decimal form, we get 4I hat plus 6.93 J hat. And these are measured in this problem in inches. So R1 we have in component form. Questions on finding R1? So we want to do the same thing with R2, again breaking it down into its components. We want to pay attention on this one. Actually, two things going on. We want to see how much of R2 is along the x-axis and how much is along the y-axis. So if we do this as kind of a set of instructions, we can go up and then we can go to the left at a right angle to get from the origin to the end of R2. So what will be the I component of R2 using the given information here? So two things are different about this. So I guess what's one thing that's different from between the x component of R2 and that of R1? Yeah.
It's in the second quadrant?
Right, it's in the second quadrant, meaning, according to our coordinate system, it should have a negative x component and a positive y component. So whatever we find for the x component, and we can see when I draw it up here, that part of it faces to the left, which is the negative x direction. Therefore, the I component is going to be negative. And that's crucial to make sure that it's in the correct, it's either along the positive sense of the axis or the negative sense of the axis. And then how large will it be? We know it's going to be negative, so what is the length of that piece? So it's using assuming we want to use the 70 degrees for this exercise we do. We don't want to use, why do we not want to use the cosine of 70?
That's the y.
Right, in this case, cosine, if we look at this 70-degree angle, cosine uses adjacent, but the adjacent in this case is vertical. The opposite in this case is the horizontal. So what you don't want to do in 2D or 3D, don't just assume you use cosine because it's the I hat direction and sine because it's the j hat direction. It's going to be dependent on how the information is presented to you. So in this case, we could have drawn that 20 degrees there, and then it would be cosine of 20. But if we want to use the 70 degrees, that's the opposite of the 70 degrees. So this is going to be sine 70. Now, cosine 20 and sine 70 are the same, so it doesn't change the numerical answer, but we just have to be careful that we're using the correct trig function. So again, the horizontal component, if we use the 70 degrees, that's the horizontal, is the opposite. So -6 sine 70 is the I hat component. The j hat component, again, we're in quadrant 2, and we can see that it's pointing with the positive y direction. So this will be a positive component. Relative to the 70 degrees, that vertical leg is adjacent. So here, for the j component, we'll use 6 cosine 70. And in decimal form, we get -5.64 I hat plus 2.05 j hat, also in inches. So again, negative because it's in quadrant 2 for the I hat, and positive on the j hat. And that will make a difference when we go to find the resultant, because if this were positive, we're adding two positive numbers together rather than positive and negative. Now we can carry through this addition because we have ij components. To find the resultant, we'll have 4 minus 5.64 is going to give us a negative 1.64i. And the 6.93 plus the 2.05, those are both the j components, are going to give me, I think I rounded a little bit, but 9. If we draw a picture of our resultant force here, well, one thing is if we did use from physics the tip to tail method, if this were drawn to scale here, this would be that resultant vector. We got the same thing using the math in Cartesian form rather than graphical form. But we can still draw this or really sketch it in our Cartesian plane. So these were the two applied, or the two R1s, R2s. This is what our resultant vector looks like. It's negative 1.64 in the I, so it's going to be in quadrant 2. So we know at this point what the components of it are. Now what we want to find is the polar form of it, so we need to know the magnitude and the direction. But again, direction, unless otherwise stated, is going to be measured counterclockwise from our positive x-axis. For this sketch, I usually leave the signs, the SIGN signs off of it, and then just go back to the geometry here. So I have the component form. I need the polar form of it. I can find the magnitude of r by taking the square root of the squares of the components. So this vector will have a magnitude of 9.13 inches. And then for the angle, I want to be careful here because it is in quadrant 2, and this is how I know it's going to be, first of all, an obtuse angle. But the easiest thing to do is if I'm just using regular trigonometry, I can't find theta directly as easily. I prefer to find that inside angle and use that to find my outside angle. Whether I'm in quadrant 2 or 3 or 4, making this sketch is really going to help make sure that the angle you're finding is the correct one. So if I first find what I'm going to just call beta here, again, just treating this as a geometry or a trig problem, it's going to be the opposite of that angle beta over the adjacent. And for this step, I'm going to ignore any of the signs that came out in this step. So I'm just going to treat it as a triangle that has a leg of 9 and a leg of 1.64. So beta is going to be 9 over 1.64, the arctangent of that. The value of beta I get is 79.7 degrees. And again, that's the inside angle, but the theta is the outside angle. But from the sketch here, I know that beta and theta are supplementary. So therefore, theta is 180 minus 79.7, or 100.3 degrees. Again, we know it should be obtuse because we're in quadrant number 2, so it has to be greater than 90 degrees. Questions on finding that angle theta. Right, putting this together to find the polar expression for arc, it's going to be its magnitude, 9.13, at an angle of 100.3 degrees in inches.